are going to discuss about the basic concept of maxima minima of a function and area under the curve. So now let us draw a function y equals fx. Let's say the function is like this. So from our previous lectures we discussed the concept of slope, and we need to analyze the slope of the function at different points. So basically, if a function is like this, y equals to fx, we draw tangents at this point. We see that the slope is high at this point. Now as we increase x, the slope decreases, and as we increase further, the slope further decreases, and at this point the slope becomes 0, and again at this point the slope is like this, and this point the slope increases, this point the slope is much more, and like this. So we see slope first decreases, and goes to 0, and then again increases. So we see that for a particular point the slope becomes 0. So the point at which the function has a slope 0 is a critical point. That is dy dx is 0. That is, the slope is 0 at x equals x1, say. x1 is 0. So the point has a slope 0. Now this is a maximum case. The function is attaining a maximum value at this point. Similarly for minima, y equals fx, the slope is first more, then becomes less and comes to 0, and then again increases, as you can see. So in both cases dy dx at x equals x2 is 0. So how will we analyze if the function is having a maximum or a minimum? Then we need to see the rate of change of the differential, that is the tangent. So we do d2y dx2, and why are we doing this, I will tell it. Just for this case d2y dx2 must be greater than 0, so it is a local minima, and for this case d2y dx2 less than 0, local maxima. So this is the case, and we will use this property to judge if the function is attaining a maxima or a minima. In this case, first we see that the slope is decreasing, and then it is going to a point which is a slope 0. So in this point x equals x1, x equals x1, dy dx is 0. So we note this point. Again we move, so the slope is increasing, as you can see, and then from here the slope is decreasing, and here it goes down to 0 again. Let's say this is x equals x2. So here also dy dx is 0. So again we see slope is increasing, and again from here slope is decreasing and attaining a slope 0 here at x equals x3. So at x equals x3, dy dx is also 0. Now how will we say what is the behavior of this function at these three critical points? These are the critical points. So as I told you, without any reason or proof, just stay to this fact that d2, if d2 by dx2 is less than 0, it is a local maxima, and if d2 by dx2 is greater than 0, it is a local minima. So now we can see from the graph that this point is neither a maxima nor a minima, but having a slope 0. So this point, since I have drawn the graph, there is no need to analyze the function with its differentials. I can see it directly from the graph that this point is a point of inflection. So those points which has a slope 0, that is dy dx is 0, and the second order differential is also 0, then those points are called point of inflections. So this point is a point of inflection. This is a x equal to x2 is a maxima, as you can see, and this is a minima. So if you are given any function and asked to find the critical points, then you do dy dx is equal to 0, and if the second order differential exists, then see whether at that point the value is attaining a negative value or a positive value, and accordingly the point will be called a maxima or a minima. Note that the term maxima is localized, that is, it is valid only for a particular interval, like this. There cases may also exist that a function has more than one minima or more than one maxima, like this. So here we cannot predict which is the most maxima of maxima, that is the global maxima, or the minima of minima, that is the global minima. We have to find every critical points for every intervals, and we can say that between this interval, this is the minima or this is the maxima. To find the global minima or global maxima, we need to first find all the critical points, then analyze them and find the second order differential, and then find the value of the function by y equals fx, then say x1, x2, x3 be critical points. Then we analyze what is y for x equals x1, so what is y for x equals x2, and what is y for x equals x3, and then we compare which is the maximum of those three values of y. So that will be the global maxima. So this is the case of maxima and minima. So now we come to area under the curve. What is area under the curve and what is its geometrical significance? And by finding the area of the curve, what we actually get? So let's say we have a function y equals fx. We want to find the area under the curve. So what will we do? To find the area of the curve, we use the technique of Riemann integration by dividing this interval. We have to specify some interval x equals a to x equals b, and divide this interval into infinitely many strips of length tending to 0. So we take infinitely many strips, like let's say n strips where n tends to infinity, and each interval has equal length. we take infinite strips each of equal lengths and then divide the interval. Now we find the area like this. If this length is very small, then we can consider it as a rectangle. See, this can be considered as a rectangle, and the remaining portion of like this small triangle is having a very small area, so we neglect it. Now also I will show you, this is a rectangle, this small triangle's length is not considered again. So this is a rectangle, this is a rectangle, only this rectangle's areas are taken into consideration. So the first rectangle is of height, say this is A, so f of A into, let's say this length is del x dx, each length is dx. So each interval of has equal length dx. So f of A into dx is the area of the first rectangle, plus f of A plus, let's say dx into dx, sorry, f of A plus dx into dx, yes, plus f of A plus 2dx into dx plus f of B into dx. So now also I want to tell you something, that this can also be written in another form, like B minus A equals n dx, because B minus A is this length and this length is divided into equal lengths dx n times, where n tends to infinity. So n into dx is actually the length of the interval. So B minus A equals n dx. Now A can be written as, B can be written as A plus n dx. So it comes as a arithmetic progression series. So this is nothing but, so this strip, the last strip is of x equals A plus n minus 1 dx, because B is B equals A plus n dx, but this strip is the previous strip, so this x is A plus n minus 1 dx. So A plus n minus 1 dx, and we if we start calculating the area from this first strip, we call this technique Riemann integral technique, is type of lower integral type. This type 1, this is called type 1 lower integral. So we can formally write this is approximately the area of curve. So approximately this is the area of the curve, and mathematically writing it, it comes out to be summation of f of A plus k minus 1 dx into dx, k rising from 1 to n. This is actually giving us area of curve. So now this can be written as so this is the discrete points, and if this function be continuous function, then we write it as integral fx dx, x rising from a to b. This is the lower limit, this is the upper limit, and this gives us this, because first we take a, x equals a, and then calculate fa dx, then we take some length, then calculate that. So summing them up, we actually get the area under the curve. Now we calculate this by lower integral type. So now we will calculate by upper integral type, that is at the b end, towards the b end. That is, we'll now do like this. We'll take the area from b, f of b, that is, if this is x equals b and this is x equals a and this is the function, so first we started from x equals a and calculated the strips area and summed them up. Now we take from the x equals b end, that is, we will have the first rectangle like this, then the second rectangle like this, then the third rectangle like this, the fourth rectangle like this, each of equal length dx, and we in divisions equal length dx and started from x equals b. So when we come to the end, we'll have this, the previous one like this and this. Now you see that we are calculating the area of the curve. Now first we take this rectangle, this first length is f of b into dx, so f of b into dx plus f of b minus dx into dx, plus we continue like this, and last rectangle, this rectangle has a length of f of, last rectangle we are writing b minus n minus 1 dx into the dx. Also you can see that this is nothing but b minus n minus 1 dx. So you can see, if we sum them up, summation f of b minus n k minus 1 dx into dx, k goes from 1 to n, where b minus a by n equals dx. This holds for the upper and also the lower. So we are doing the upper integral type. So we can say it again as this. So both of the upper integral type and lower integral type are giving us the approximately the area of the function, but not exactly, because you can see that these triangles are having some extra lengths in case of upper integral type, and previously the diagram I showed you, that is, I am drawing it once again, the same function y equals fx, and if we do it lower integral type, then we are starting from x equals a and then continuing. So you see some areas are left out. I am drawing it clearly. You see some areas are left out. Some triangles are left out. Drawing it bigger. Some triangles are left out. So the lower integral type is giving us a lesser area than the actual area covered by the function, that is actual area under the function. And the upper integral type is giving us somewhat more than actual area under the curve. So we can use a technique here to say, actually, let's say, so I'm writing it here, integral fx dx so now we see that the actual area of the function, that is integral fx dx from the lower bound a to upper bound b, x equals b to x equals a, is actually lesser than the area of the function, area under the function for the upper integral type, that is summation f of b minus k minus 1 dx into dx. K goes from b to a, k goes from 1 to n, and then the area, actual area of the function is greater than the lower integral type, that is summation f of a plus k minus 1 dx to dx. K goes from 1 to n. Okay, so you see that the by squeeze theorem, if this limit of this, if dx, if del x tends to 0, then the area actually gives us the area under the curve. This area is also approximately, as the error will decrease as much as you will decrease dx. So if dx is very small, then the error will be very small. So this will also give us the area of the function, area of the curve, area under the curve, area of the function under the curve. This will also give us the area of the curve, area under the curve. So we see that this lies in between these two, and as you minimize dx and as dx tends to 0, all these three merges to the area under the curve. So this is the actual significance of the area under the curve of a function.